Hi there, welcome to video lecture 3, Working with Formulas. Today we're going to look at equations that contain two or more variables and be able to rearrange them to solve for them more efficiently. Notice in this example we are solving for Fahrenheit given Celsius temperature. But what if we want to find Celsius given Fahrenheit temperature? Well, we could plug in our values of Fahrenheit here and then rearrange the formula each time, or just once rearrange this formula to solve for Celsius in terms of Fahrenheit, and then plug in our values a little bit more easily. So let's do that. If we look at this formula, F equals 1.8, and remember, there's no operation between the variable and the coefficient. It always implies multiplication, plus 32, so we have 1.8 times C plus 32. What I'm going to do is try to focus on the easiest thing to do first, remembering that all of our rules for solving equations will fit here because these variables represent numerical quantities, hence hold the same properties. So the first thing I'm going to do is get rid of that 32 and bring it over to the other side. So notice what happens here. We're left with F minus 32 is equal to 1.8 times C. Now, since that 1.8 is being multiplied to C, we know that division undoes multiplication. So I'm going to divide both sides by 1.8. And in fact, we can leave our answer just like this. And that's how we get this new working formula for Celsius. Celsius equals F minus 32 divided by 1.8. A lot easier to work with every time if we've got to do a bunch of conversions. Now remember, just something to keep in mind, always imagine that there's an implied set of parentheses around your numerator. You have to work that out first before dividing by 1.8. All right, let's move on. So now what we're going to do is work in reverse here. Notice that in the last problem, we started with F equals 1.8C plus 32. Now let's just go backwards and make sure that we can get back to this original formula just to get a little practice of rearranging these variables. So we're starting with F minus 32 divided by 1.8 equals C. If you look at this problem, let me explain why we're doing what we're doing over here to the left. Notice that this 1.8 sits in the denominator and kind of locking these guys in place, not allowing us to be able to move that F minus 32 anywhere. So if we multiply both sides of the equation by 1.8, we can remove it from the denominator and now yields a new equation, F minus 32 equals 1.8C. The last thing we want to do is look at the fact that this 32 is being subtracted from F. So we can undo the subtraction by adding 32 to both sides of the equation, leaving us with F equals 1.8C plus 32, right back to where we started. One thing I want to make you wary of here, be very careful, is that you're not always solving and getting an answer. In fact, with formulas, we're not until we plug in given values for our variables. Here, all we're doing is rearranging this equation to look differently to make it easier for us to work with it. If I told you that Celsius was, in this case, let's say, for instance, 37 degrees, then we could plug in 1.8 times 37 plus 32 and yield a Fahrenheit value of 98.6 degrees Fahrenheit. You have to be given something for that variable in order to do so. All right, let's move on, apply this to some other formulas just to see how this works. So something we've discussed in class is IV flow rates. In fact, we've gotten some practice with this not too long ago. Well, to calculate an IV flow rate, we take infusion volume divided by time, and we multiply by the drop factor. And that drop factor comes right from our IV tubing set, and it is expressed always in terms of drops per milliliter. R, what we're trying to solve for here, given this original equation, is our flow rate in terms of drops per minute. So now let's take this formula, V over T times C equals R, and let's look at part A. We want to solve for T, which just simply means we want to get T by itself on one side of the equation. Notice this has similarities to one of the problems we just looked at. T is stuck in the denominator. So we're going to multiply both sides by T to get it out of there. And that's going to yield a solution of V times C equals R times T. Now in the first part, we want to go ahead and solve for T. So notice this R being multiplied to T is keeping us from doing that. So let's divide both sides by R to get T completely by itself. And what we're left with is T equals V times C, or C times V, doesn't make a difference, over R. And that's our first solution for part A. Now let's go ahead and solve for our infusion volume, V. Notice that this is going to be set up very much the same as what we just saw a moment ago. We're going to start with the same original. In fact, we're going to get to the same working equation that we just saw. So now we have our original equation, V over T times C equals R. Let's go ahead and get rid of the fact that that T is in the denominator because it's keeping V from being moved about and really keeping V from being isolated by itself. So now we end up with V times C equals R times T. Notice we got the same thing just a moment ago. Before we divided both sides by R, now we want to get V by itself, so we're going to divide by C in order to do so. And what we see here is that we get V equals R times T over C. All right, so we have our working equation for part A and part B. And let me just move this up here and put it in the right place. So here, T equals V times C over R, or if we're looking for infusion volume, V equals R times T over C. So notice in part C, let's see which formula is going to be the best to work with. Well, if you notice, we're asked to find, given the information, the infusion time. So we're going to take this formula. T equals V times C over R. Now let's plug in our variables. Well, here's our V, 250 milliliters. That's our volume to be infused. And notice that this is an IV containing heparin. Now we have to find our C, and that's our drop factor. And notice it tells us the infusion set is microdrip, which means the drop factor is 60 drops per milliliter. Now we're going to divide that by, in this case, R, our infusion flow rate. And that's given to us as 40 drops per minute. What's nice about setting up these problems is that you should see the units cancel that should go, and the units that should remain should be what we're solving for. Notice milliliters over milliliters, drops over drops, and we're left with minutes. So if we work this out and grab your calculators, let's go ahead and calculate 250 times 60 divided by 40, and that gives us 375 minutes, which if you divide by 60 is equivalent to 6.25 hours, or we could say 6 hours and 15 minutes. All right, looks like we're ready to move on. Excuse me. So now let's work out the Fahrenheit equation. Now let's imagine instead of given 1.8, we were given a coefficient in the form of a fraction. This does change the way we approach the problem because now we're having to deal with a fraction instead of a decimal. So let's go for it. We have F equals 9/5 C plus 32. Think for a moment of what's the best way to get this done. Well, would you want to multiply everything by a fraction or start by subtracting? So I would say start by subtracting. That way we only have to work with multiplying by a fraction once. So we're going to divide, we're going to subtract both sides by 32. And we're going to undo the fact that that 32 is being added to the right-hand side of the equation. And notice this looks very similar to what we saw a few moments ago, except 9/5 is being replaced with, or I should say 1.8 is being replaced with 9/5. It's equivalent. Now, anytime we have a fraction being multiplied to a variable, remember what we can do. We can divide by that fraction, or more easily, multiply by its reciprocal. And if you're going to multiply the left-hand side of this equation by its reciprocal, 5/9, make sure you multiply everything. And the way we can do that is by using parentheses to show that entire expression is being multiplied by 5/9. So our new formula, 5/9 times the difference between the Fahrenheit temperature and 32 degrees, will yield our Celsius result. And there's our formula. Nice. All right, now let's look at this business application. And this one's interesting. I like this because many of you will be involved in business to some degree. And for that reason, it's good to talk about total cost and looking at how costs are accumulated based on how we produce something or how we utilize something. You can apply this to anything. This works if you're like me and you like to rent videos on demand. You have variable costs, your on-demand price per movie, but you also have your fixed cost, which is your monthly rate. We can figure out the total cost per month and get a sense of what we would be spending should we watch, I don't know, 5 or 10 movies a month. Here we're going to look at it from a production standpoint. So total cost is always equal to variable cost times the number of items produced, bought, sold, whatever, plus the fixed costs. And those are the costs that don't change regardless if you make 10, 30, 50, or 1,000,000 units. So let's go for it. And let's plug in the values of this formula. The formula is already given to us. And here what we're going to do is figure out how many sets of forceps were produced. Now we could work with this formula and actually look at how to solve for x, or we could plug it right in. I'm going to go ahead and do what we've done already and break down this formula. So we have total cost equals variable cost times x plus fixed cost. Let's do what we've done in the problems before and subtract that fixed costs from both sides of the equation. So I'm just going to call it FC over here, minus fixed costs, minus fixed costs. I'm going to write it out a little bit better here. Now notice, in doing so, these guys go away, and we're left with total cost minus fixed cost equal variable cost times x. So in order to get that x by itself, we're going to have to divide both sides by variable costs. That's going to leave us with x, and in this case, that represents the number of items produced. So let's read the problem. A local surgical tool manufacturer produces hemostatic forceps used to control blood flow during surgery. The company spent $1,100,000 to produce forceps in 2014. So there's our total costs. If it cost $850 to make each set of forceps, so notice $850 per set, that's variable. It varies depending on how many sets are produced. So that's our variable costs to make each set of forceps. And the company paid $250,000 in fixed costs, so we know what that represents. How many sets of forceps were produced by this company in 2014? So let's plug it in. We have 1,100,000 minus our fixed costs of 250,000 divided by our variable cost of $8.50 per set, and that's going to give us what we're looking for. We're looking for x, the number of sets of forceps produced. All right, so let's do it. And I'm going to grab my calculator to check my results. And when you work this out, you should get a value of 100,000. It's always good to express this with the right unit. We're not looking for dollars here, but instead sets of forceps. So 100,000 sets of forceps were produced in 2014 based on these numbers. All right, moving on. Let's look at a very important equation in order to determine body mass index. We have BMI equals weight divided by height squared times 703. I'm going to make life a little easier and make this formula a little bit more concise. Weight divided by, I'm going to just put it as a fraction, height squared times 703. So now notice in the first problem, we want to go ahead and solve for weight. So if we look here, let's think about what's keeping us from doing so. Right now we have BMI, just to give myself a little more room here, equals weight divided by height squared times 703. We're trying to solve, in this case, part A wants us to solve for weight. So notice we've got two things happening to weight, keeping it from being by itself. Height squared is being divided into it, and 703 is being multiplied to it. Now you can do this all in one shot, or you can take it step by step. If we get rid of that height squared in the denominator, we can start getting weight closer and closer to being by itself. So now we have height squared times BMI is equal to weight times 703. Now we want to get that weight completely by itself, and that 703 being multiplied to it is keeping us from doing so. So let's undo that with some division. Now notice what we've got. We have a working formula for target weight. If we have a target BMI that we want a patient to achieve, we can now say this is the target weight to get there based on their height and their target BMI. So weight equals height squared times BMI over 703. So let's put that back upstairs here. And we can say that weight is equal to BMI times your height squared divided by, clean that up a little bit, 703. So now in the next problem, we have a 5'9" man, 5'9" man whose BMI or target BMI is 26.4. Let's say that in this case, that's the given BMI. What would be this patient's weight based on his height and BMI? Well, the first thing we have to do is convert our feet and inches to inches, if you remember. So here, 5 feet, well, that's 60 inches plus another 9 inches. It's going to give us 69 inches. And our BMI is stated as such. So here's our height and our BMI. And I'm just going to keep units out of here because they don't really cancel like we've seen in other formulas. They do, but it's a little deceiving based on what's built into that 703. So we have BMI 26.4 times height squared, 69 squared, divided by 703. So go ahead and work that out. And what you're going to find, take a second. Is that you get approximately, if we round to the nearest pound, 179 pounds. That would be this man's weight given his height and BMI. All right, now it's your turn to try some of these problems on your own and make sure that you can tell the difference between solving an equation like we've seen in previous videos versus actually rearranging a formula to solve for a given variable. All right, why don't you pause this and work through these and then we'll review them together. Okay, if you're ready, we're going to start breaking down these problems together. I'm going to start with number 1. Number 1 asks us to solve our equation for x, and what's given to us is -3 times x minus 4 is equal to 2x minus 6. Notice we are solving an equation. We're trying to get a value for x. We are not rearranging a formula. How do we know this? Notice there's one variable in this equation, and it's asking us to solve for that given variable. So if you remember, the first thing we have to do in a problem like this is get rid of these parentheses by distributing, and be careful of signs here. We have -3 times x minus 4, which gives us -3x. Negative times negative is plus 3 times 4, which is 12, is equal to 2x minus 6. So now I'm going to follow the same rules as the last video and get those x terms to the left by subtracting 2x from both sides, bringing it over to the left-hand side, leaving us with -5x plus 12 is equal to -6. Now I'm going to bring those number terms to the right-hand side of the equation by subtracting 12 from both sides, leaving us with -5x equals -2x 18. Now that x, let's get it completely by itself by dividing both sides by -5. Make sure you take that sign because it's the -5 that's being multiplied to the x. Don't accidentally add 5 to both sides. So when we work through this, what we see that we get here is 18 over 5, which can be represented as 3.6. So going back here, our first answer, x equals 3.6. Now, if we look at 2, notice that this is a proportion, so we can use cross products to solve. So let's do it. And I'm just going to make a little space here. Work through that problem. All right, nice and clean. Okay, number 2. We have a plus 6 over 5 is equal to 3 over 8. So let's use our cross products to solve this. Notice that 3 times 5, be careful here, this entire expression is being multiplied to 8, is equal to a plus 6 times 8. I'm going to write that a little differently. I'm going to write it as 8 times a plus 6 to make it easier to distribute. At least I feel like it's easier. You may be fine with writing a plus 6 times 8, your preference. So we have 15 equals, and if we go over to the other side, we have to clean up this side as well by removing those parentheses through distributing our 8. 8 times a is 8a, and 8 times positive 6 gives us 48. Now this looks pretty traditional. I'm going to do something a little different. Since our only variable terms on the right-hand side, I'm going to bring those number terms over to the left-hand side just to make life easier instead of having to have a lot of steps built into this process. Now we've got 15 minus 48, which is negative 35, and that's equal to 8a. And here, lastly, what we're going to do is divide both sides by 8. So we can get that a completely by itself. And you can see here we get a equals negative 35 divided by 8. And you can always leave these answers in terms of, whoops, I made a mistake. Did you catch my mistake here? This would not be negative 35. 15 minus 48 is actually negative 33. So my apologies here. So 15 minus 48 gives us negative 33, not negative 35. So I revised that, and now what we have here is a equals, accurately stated, negative 33 over 8. And go ahead and use your calculators for these. Don't feel like you need to leave everything in fraction form. You can, but here this is improper, so why not just go ahead and work this out as a mixed number or a decimal. In fact, if we plug in negative 33 divided by 8, we get negative 4.125. And remember that you can always check your answers here, and I suggest that you do. If you take negative 4.125 and you add it to 6 and divide that sum by 5, it's going to actually work out to giving you the same answer as 3 divided by 8. So we're looking good here. All right, let's move on, and now let's talk a little bit about formulas. So here we got a equals negative 4.125. Now notice this problem. We're not actually going to solve for a given variable. Instead, we're going to rearrange this formula and talk about it in terms of y as opposed to 3x plus 2y equals 16. So let's do that. So number 3, we have 3x plus 2y equals 16. We want to get y by itself, and my apologies, this should be a plus. 3x plus 2y equals 16. We want to get y by itself, so this 3x that's being added to 2y, let's go ahead and remove that first before we divide anything by 2, just to make life easier. And what we're left with is 2y equals 16 minus 3x, or I can write that as negative 3x plus 16. Either way is fine, but this is a pretty standard form that we're used to seeing. Now, in this case, I'm going to divide both sides by 2 to get y by itself. And we can divide this entire expression by 2, or we can divide each individual term. And the reason that I want to divide each individual term by 2, I'll share with you in just a moment once we look at this new equation expressed in its form. Negative 3 over 2 times x is the same thing as negative 3 over, x over 2, plus 16 over 2 is equal to plus 8. Now, when you look at this problem, notice that this has a similar form to slope-intercept form, y equals mx plus b. It's a pretty standard type of linear equation where our y-intercept is what we're adding, and our slope, our rate of change of this function, is given to us as the coefficient in front of the x. That's the only reason I chose to divide each individual term by 2, and it allowed me to reduce the 16 over 2 to look a little more clean. So that's up to you. Not a big deal, but if you're dividing by a negative, it might be a good idea to do that so you can clean up that negative outside of the denominator. So let's just go back and write our answer. Y equals negative 3/2 x plus 8. All right, so we are getting there. So now let's go ahead and look at number 4. In this case, we want to solve for the formula final velocity. And we know that acceleration is equal to final velocity minus initial velocity over time. I'm just going to clean up some space here. Sorry guys. So I can show you what to do here. Think about what we've done before to rearrange these formulas. Once again, now in this case, we've got 3 variables. Actually, we've got 4, don't we? But we're going to get 3 variables on one side of the equation. So this is number 4. And what we are looking for in this case is final velocity. So we have acceleration equals final velocity minus initial velocity over time. This is a physics equation. In order to figure out the rate of change of speed, we're going to just subtract those speeds from each other and divide by the time it took to increase from one speed to the next. So to get VF by itself, notice that T is stuck in that denominator. So what we're going to do is multiply both sides by T. Get it out of there. And that leaves us with, I'm going to write this how we usually write algebraic expressions in terms of alphabetical order. So now AT is equal to VF minus VI. Now we're trying to get VF by itself, and this VI being subtracted is keeping us from doing so. So we're going to add VI to both sides of the equation. And what that leaves us with now is VF is equal to AT plus VI. So we had a lot of variables in that one, but it wasn't that bad to move around and solve. All right, let me go ahead and put that back in the solution set here. So VF is equal to AT plus VI. All right, one more here. We want to solve for that we want to solve for that F. And notice that this looks very familiar to what we've seen before, except once again, we're expressing this formula in terms of a fraction. So let's do it. Our last problem. Just going to go ahead and clean this up. Give us a little space here so we can do what we need to do. All right. Nice and clean. Okay, so here we have C equals 5/9 times F minus 32. I'm losing my marker here. All right, sorry about that, guys. So notice we want to get F by itself, and it's stuck inside the parentheses. We could distribute by that 5/9 to clean up everything inside and get everything basically set free by removing the parentheses. But I want to show you an easier way. If we multiply both sides of this equation by 9/5, we can remove the fact that that 5/9 is being multiplied on that right-hand side of the equation. So notice what I did here to be sneaky, or at least efficient, is multiplied each side by the reciprocal of 5/9, leaving us with 9/5 C is equal to F minus 32. Now we're almost there because we just want to get that F by itself. So I'm going to go ahead and add 32 to both sides of the equation to get rid of the fact that it's being subtracted from that F, leaving us with 9/5 C plus 32 is equal to F. And that makes sense because we've seen that if we take 1.8 times C plus 32, it'll give us our Fahrenheit equivalent. And 9/5 is actually equal to 1.8. So let's just put that back here. So F is equal to 9/5 C plus 32. All right, guys, that's it. I hope this helps you and prepares you for your solving formulas homework worksheet. If you have any questions or want to validate a result, don't hesitate to send me an email or stop by the Math Lab to get those questions answered quickly. Thanks so much.